For today, I want to talk to you about dynamic arrays. Okay, so you might think arrays. We already, what is there to learn? It's just a simple data structure, right, with a bunch of slots. Each one of them is fixed width. You can store some primitive data type in each one of these slots. Right, these can be integers or floating point numbers. You can also store pointers to other more complex data types. Right, you can put an element in any slot in the array using a random offset. Right, and then you can get the data item by referring to that offset and doing a random access and getting that data item. Okay, so I also thought that I knew everything there is to know about arrays, but it turns out I didn't. And this course reflects a lot of learning that I've actually done over the past 2 or 3 weeks. So this is new stuff that I'm kind of excited about. Hopefully I'll get you excited too. Okay, so here's a problem we're trying to address. Problem is, at some point your array fills up with data. And well, as you know, if you try to access an array out of bounds, if you're using a same language like Java, you're going to get an error message. If you're using a slightly less same language like C++, you'll get spooky undefined behavior, which means you can't really predict what's going to happen. All right, and to overcome that, what do? Not a trick question. Yep. You resize. Okay, and how do we resize? The typical thing that we do is we allocate a new array of twice the size. We're going to copy everything from the first array, into the first half of the new larger array. And this is going to, we'll deallocate the old one, and this will allow us to, add more data. So we can kind of continue doing that. Seems to be easy. In C++, you have options for allocating static arrays or dynamic arrays. So this is how you'd allocate the static array. Here's the dynamic array. Let's focus on the dynamic arrays. So here's an example of what happens in a dynamic array in C++. Here's just an example of pushing elements back to the back of the array. And this data structure from the standard template library, it's going to expand automatically for you as you push to the back. Okay, so if we run the following code, this is code that, as you're pushing back, you're measuring, So this pushback is going to resize if we exceed capacity. And here, this code is just measuring the number of elements that are in the array and the capacity, And you will notice that as we add more and more elements, the capacity here is increasing, So here it's jumping from 1 to 2, 2 to 4, 4 to 8, 8 to 16. It's increasing by a factor of 2 every time. Okay, even if the number of elements is smaller, the capacity is still growing by a factor of 2 each time. Okay. So, so here's an interesting design decision. So we have this growth factor of the array. We do have some choice in how to tune it, So the C++ vector does it by a factor of 2. But let's ask you a question. So what happens if I set the growth factor to be either too high or too low? Let's take too high first. What happens if I set the growth ratio to be too high? What kind of undesirable thing happens?
You're wasting a lot of space.
Wasting space, yeah. Exactly. What happens if it's too low? Yep.
You have to copy more times.
You have to copy it more times, exactly. Okay, so say the size ratio is 4. So right after expansion, here's the issue. I'm wasting 4x space of the new array capacity. Okay, so so let us define a term. The term is space simplification. Some of you have already seen this term. And this is measured as the amount of physical space used by the array divided by the amount of data actually stored in there. So right after expansion, your space simplification is actually equal to the growth factor, In this case, it's 4. So this is right. This reflects space simplification right after expansion. If you actually want to reason about max space simplification, you can do that too. So during the expansion, you're actually wasting more space. Because during the expansion, the old array still exists, So at that point, if you want to measure that kind of worst case space simplification during expansion, that's going to be G+1, actually. Okay, because that one is just reflecting kind of the old array. All right, what happens if our growth factor is too low? So let's say we set it to 1.5. In this case, right, insertion overhead is going to increase because every entry on average will participate in more expansion operations, and during each expansion, we're copying all the data elements in the array. Okay, so you can model that overhead too. Let me call that write amplification. So many of you will have seen that term as well. This is defined as the number of physical writes you're doing. So the number of, basically it's like the average number of times you're copying each data item, right, kind of divided by the number of data items that you actually have. And in this case, right, this is actually, for these arrays, this is the growth factor G divided by G minus 1. And I'm not going to go into the derivation, but this is something that you derive by just taking the sum of a geometric series. Okay, so you can reason about this yourself. Okay, so we have a trade-off. This is a trade-off between space amplification and write amplification, governed by the growth ratio. Here are their cost models, and you can plot them as a trade-off curve. Right, and it seems like we would want to be kind of as close to the origin of this graph as possible. So right, a growth factor of 2 seems to achieve a pretty good balance. Okay, so all right, that's the end of the lecture. We can go home, except for not quite. This is all stuff that you know. So now we'll get into stuff that maybe you don't know, or maybe you're just vaguely familiar with. Okay, so we're going to look at two different kind of parts for this lecture. First part is about how to reuse space taken up by previous versions of the array that you've already deallocated. We'll see that there's an issue there if you're not careful about the growth ratio. And then, right, we'll introduce some indirection technique to actually fundamentally improve the trade-off between space amplification and write amplification. All right. Okay, so here's the issue. Let's suppose we're using a growth ratio of 2 in this example, but it could also be anything higher than 2. Okay, so a bunch of expansions happen. Right here, 3 expansions happen. At the point that we're here, right, all of these are previous versions of the array that are now deallocated. But once we deallocate them, they don't actually automatically disappear. I mean, it's possible the memory allocator is going to reuse them for something else, but let's actually suppose for a second that the only thing that the memory allocator has to deal with is just our array. So then there's a question: can the memory allocator actually reuse the space that we have managed to free using these deallocated versions of the array? Can we reuse that space? So what's your take? Can we reuse that space with a size ratio of 2? Does anybody have an intuition? Mm-hmm.
So let's say like we can insert the first any insertion to the first the smallest size, and then move to the next one. It delays the expansion.
You're proposing a mechanism to delay expansion by how again?
Using the
Oh, okay. Interesting. It's an interesting idea. I guess that once we've deallocated, so this would require us to be able to kind of, right, this would require us to actually keep all of these arrays alive and kind of reuse them. It's an interesting idea. The issue is that, let's suppose for now that we don't actually have access to these, right? We've deallocated them. So this is now kind of dead space that is managed by the memory allocator. And what we hope is that the memory allocator will allow us to reuse that space, but we know, let's suppose that we don't no longer have access to it once we deallocated them. So there's a particular problem I kind of want you to see. What can you say about the size of the new array relative to the cumulative size of everything that you've previously allocated? Yes? Huh? It's always one bigger. Exactly. It's always one bigger in the case of a size ratio of 2. Right? So yeah. So if you're going to sum these up, you're always going to see that it's going to be one bigger if you're using a size ratio of 2. And if you're using a larger growth factor, it's going to be even bigger. What does that mean? That if you're allocating your array contiguously, there's never actually a point where you can reuse the deallocated space. Does that kind of make sense to people? Okay. Okay, so so this implies that actually our space simplification is higher by a factor of 2 because we have a bunch of dead weight space that cannot be used for anything else by our memory allocator. Okay, we can model that. So we can model space simplification right after expansion. So right after expansion, a half of our new array is going to be used. We can assume that all of this stuff is going to be unused, unusable by the memory allocator. And the second half of the allocated array is also going to be unused. Right? If you take all of these parts and kind of divide them by the amount of used data that you have here, right? You can get a new expression for space simplification that actually takes all of these overheads into account. And it turns out that's higher than what we had before. Right? So it's this expression, right? Simple. You can simplify to this. And in the case of a size ratio of 2, turns out you're actually wasting 4 times the space right after expansion. Okay, not ideal. Not ideal if you want to be conscious about space. Everybody okay? Cool. Well, let's now suppose the converse. Suppose we are using a very small size ratio. Let's suppose we're growing it by 20% each time. Okay, so a bunch of expansions happen. Right? These become the allocated space. In this example, right, the amount of, so here we observe that if the size ratio is small enough, the size of the new array actually does end up fitting in the amount of the allocated space. So we see that there is some dependency on the size ratio. Right? So here we can actually reuse the space, but we observe that the size ratio was quite small here. And so in some sense, we still have some wasted space, right? It's like we could have actually expanded the array by a larger growth factor to use the deallocated space better. Okay, so that would allow us to improve our round amplification. Okay. So that begs the question, what is the best growth factor that allows us to perfectly reuse the deallocated space? I note that I'm talking about this question in the context of dynamic arrays, but this question will actually arise with many other data structures that you want to use. This will arise too if you're using a hash table or a sorted array. Let's fix some assumptions about the memory allocator, and then I think that will hopefully answer the question. Okay, let's assume that the memory allocator is doing contiguous allocation, right? So we're starting at address 0, and then as we allocate new things, right, we add them contiguously to whatever else has been allocated before. Okay. Let's also assume that whenever there is that a question?
It's contiguous, like for the extension, like if we need to copy the whole into the new array, just add to the add of the original array.
So, oh, you want to just add to the end of the original array. Okay. So that's going to be my fourth assumption. My fourth assumption is going to be that we can't actually just, that's a great question. I'm going to assume that we can't just do that just because even though I'm not showing it in this idealistic scenario where we only have our array, it could be possible that some other application wrote something right after it. Right? So we can't generally guarantee that there's going to be free space afterwards. Right? And generally, the way that memory allocators work, I think, is by kind of deallocating and copying it again. Okay. Okay. We're also going to assume that we can reuse space whenever possible, right? So if we've deallocated this part and we're trying to allocate this and it fits over here, right, we'll reuse that. Okay, here's a kind of simplistic assumption, but we're going to assume that we can, as we expand something, we can actually kind of deallocate this on the fly and kind of start reusing the space as we're rewriting the new version, right? So here we're taking this and expanding it. We're starting by reusing the space over here. And then, we're copying it and eventually, right, the thing gets expanded. Let's assume we can do that. Reality is a little bit more complicated, but let's just assume this for now because it's going to simplify some of the analysis. We can get over this, as we'll see. And also, to your point, we're going to assume that we can't expand in place just because in a general situation, something could have been allocated right afterwards. So, okay, here are our assumptions. We'll use these assumptions kind of for the rest of at least this first 1 hour lecture. Okay, yeah, so to expand something, right, we're going to be kind of copying it and then rewriting the new thing right after. Okay, do these assumptions make sense? Okay, I am beautifying reality a little bit, but I'm beautifying reality to illustrate a concept. And the concept will be useful, and you should be able to apply that concept even if other assumptions hold. Okay, let's get back to the question of which growth factor we should use to perfectly reuse the deallocated space. Okay, so what are the properties we need to hold for us to be able to do this? Something like this, but a little bit more precise. What we kind of want is for the size of the new thing to be equal to the sizes of the arrays in the previous 2 phases. Okay? Right, because if we do that, what does that mean? It means that every third expansion, right, the size of the new thing perfectly matches the size of the arrays in the previous 2 phases that we had. Okay, the other property, yes? You'll kind of see that if we just manage to reuse the previous 2, right, then there's never a case where we have the allocated space from across more than 2 phases present. So in some sense, we don't need to worry about even older versions. Okay. The other property that we need, we'll just assume that the size ratio stays the same. Okay, so in between any 2 expansions, right, the size ratio is always the same. How do we satisfy this? So now we have these kind of 2 requirements, and it's not totally clear how to actually get this to hold and this to hold at the same time, like for all of I. Yes.
You could divide by size out this one and solve it like that.
You could solve them, right? So you could solve this, and any idea what you would get if you solve it? 1.6?
Yeah.
Does that remind you of something that you might know? You just did some math now. Okay, you're right. It's 1.6, and we'll. Okay, so it actually turns out to be a special number that we're going to get here. Okay. Sorry? Yes, yes. I think I heard 2 of you mention the Fibonacci series, right? Yes, yes, yes. Okay, right. So some of you already spotted this. So let us suppose that the Fibonacci series actually reflects like the sizes of the array in each phase. Right. So what is the Fibonacci series? This is a series where we start with 2 ones, and then subsequently, every new number in the series is just the sum of the previous 2 elements in the series. Right. So we have 1, 1, 2 is the sum of these 2, 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, and so on. Right. So the Fibonacci series happens to fully satisfy this requirement, right? Kind of by definition. Does it satisfy this requirement? So this is a little bit more strange and weird, but it turns out, okay, so first of all, Fibonacci series, let's give credit where credit is due. This is due to Fibonacci, apparently the most talented mathematician of his time, lived about 1,000 years ago in Italy. And if we look more closely, sorry about this thing being here. That's a little annoying. Let's move it here. Okay, so an interesting feature about the Fibonacci series is if you take the ratio between every 2 consecutive numbers in this series, right, something interesting happens, right? So okay, so this is just an illustration. Okay, so let's take the ratio between every 2 adjacent numbers and see what happens. So if we take 1 divided by 1, 1. 2 divided by 2, 2. 3 divided by 2, 1.5. We continue going, and we continue going, and we continue going, and we see that this thing converges. right? And it converges to what you said, 6.1 something. And in fact, it actually converges into, right, the famous number called the golden ratio, right? So who has seen the golden ratio before? Probably all of you have heard about it. Good. I was quite surprised that it kind of shows up in this problem, but I was quite pleased with that. Indeed, the golden ratio is also something we can express in closed form in the following way. Let's now take a quick aside and just talk about the golden ratio generally, and then come back to the problem of resizable arrays, right? So as many of you might know, the golden ratio allows you to draw this, golden spiral where, this is just a bunch of squares that kind of subsume each other, where the edge, the length of every square is kind of equal to the lengths of the previous two squares in the series. All right, so this allows you to kind of recursively draw out this the spiral, and the spiral has been considered to be, divine and beautiful and very aesthetic across, many aspects of civilization. So you can find this golden spiral in art, you can find it in architecture, you can even find it in nature, and now we can also find it in computer science. Okay, some other cool properties that the golden ratio has. I think it's the only number that satisfies these kind of cool mathematical quirks. So apparently the golden ratio is equal to itself squared minus 1, and also to 1 minus itself minus 1. And I think it might be the only number that actually satisfies that. So these are fun, quirky properties. We'll actually use them in one spot. Okay. So this means that, right, so what happens if we expand the array by the golden ratio? Well, the golden ratio allows us to satisfy both of these requirements. So let's see what this looks like. Okay, so suppose I'm starting with, this first array. I'm now going to expand it by the golden ratio. I can't reuse the space immediately by assumption, right? So I have to allocate this one over here right after. But by the time that I'm allocating the second one, that perfectly reuses the space, right? And as we continue, right, now I'm going to allocate another one, and that one's going to perfectly reuse the space. All right, so in some sense, every second allocation, I get to perfectly reuse what's already present. Alrighty. Our right amplification isn't actually affected by this so much. It actually just stays what we saw before, except for you can now plug in the golden ratio, and then you can actually use one of the quirky mathematical properties of the golden ratio and simplify to the following expression. It's kind of cool, cute. What about space simplification? So how do we analyze that? Okay, so first of all, we can analyze space simplification right after we perfectly reuse the space, right? And if we do that, space simplification is just the golden ratio, right? On the other hand, we have this more annoying case where, every second expansion, we can't act like we have the older one, we have the newer one. We are wasting a bunch of space here. We're also wasting a bunch of space here. So every second expansion, we're wasting more space. Not ideal, but actually we're still wasting less space than before. We're wasting less space than before because we only have like one deallocated thing, not the sequence of all deallocated things across time. So we're still wasting less space here. Okay, and actually if you model that, you're going to get growth ratio +1. Okay. Okay, well, so here's kind of what the picture looks like so far. All right, okay, so suppose that we set the growth ratio to be higher than the golden ratio. In this case, you're going to see the space simplification that we saw at the beginning of class. If you set it to be smaller than the golden ratio or smaller, you're actually going to find that the space simplification oscillates between G to G+1 of every alternate pair of expansions. Okay. Right amplification just kind of stays, isn't actually altered. Okay, let's look at some, just so that you see that I didn't make all of this up and imagine it. Let's look at some array implementations in the wild and what growth ratios they set by default. So, right, so, okay, actually, I'm not sure the C++ is here, but you will see that the Java array list, for example, uses a ratio of 1.5. And various implementations use a growth ratio that's indeed lower than the golden ratio. And this is not necessarily by accident, right? It's because the people who designed these were actually aware of this quirk and took it into account. And in fact, if you look at so Facebook, Meta, has their own library of data structures. And if you look at the Facebook vector of the Foley library, follow the following link, you'll actually find a discussion of precisely everything we've seen here. Right, and why they use 1.5 as a size ratio because of this discussion and issues. Okay, so I recommend having a look at this at your own time. It's quite fun to read. Okay, this concludes the first part of the class. In the next part of the class, we're going to learn how to fundamentally overcome that trade-off between space simplification and right amplification using some other technique that is a little bit more complicated, but actually very beautiful as well. But I suggest that we take let's take a 10-minute break. So come back at 2 o'clock. Okay, folks, let's restart. Okay, welcome back. Okay, so now we're going to look. Okay, so even if we're using the golden ratio to expand the array, there's still a fundamental trade-off there between space simplification and right amplification, right? We still can't get both of these metrics to be perfect at the same time. Ideally, right, the best we can do is to have a space simplification of 1 and a right amplification of 1. That's what we would desire. But so far, with anything that we've seen, we can't. Okay, now we're going to look at how we might be able to do that. And the court, okay, and to do that, what is the thing that we need to be able to overcome that trade-off completely? The thing that we really need and desire to be able to do is to do that thing that we assume that the memory allocator does not allow us to do, and that is to expand in place, right? To just kind of add something to the end of the array and just kind of have it become a part of it. What is the promise? So suppose that we could do this for a second. What kind of right amplification would you expect? 1. Yes, 1, because we're never copying anything, right? And what kind of space simplification you might expect? We'll see. Okay, so the way that we're going to solve this is by adding 1 layer of indirection, right? So now we're going to have some directory data structure, and the directory structure is going to contain pointers to different data blocks. Okay, first of all, going to introduce a very simple way of doing it. Then we will see that the simple way doesn't actually work out that well, and then we will, kind of devise a more cool and artful way of doing it. Okay, but okay, in the simplest case, let's suppose that we have this directory, and let's suppose that all of these data blocks. So each one of these data blocks is just like a contiguous chunk of memory. It's a part of your array. Contains. Let's suppose that all of these data blocks contain the same number of slots for simplicity for now. Okay. So now, suppose that we want to do a get operation. To do that, we just divide by the data block size to find the data block that we need to go to. To get the offset within the corresponding data block, we do a modulo operation. Right. So suppose, for instance, we want to get 5. Right. This tells us, right? These tell us that we need to go to the first slot in data block 1. Okay. So far, so good. It seems pretty easy. How would we expand this thing? So,
add a new chunk to the directory, or like make the directory point to a new chunk.
Yeah, so you could actually, yeah, okay. So as long as there's new space in the directory, we can just add a data block. But then if the directory is out of space, we could just expand the directory, and we can expand the directory, by allocating a whole new copy. This is kind of okay because the directory is small relative to everything else. So this is not going to cost us very much in terms of space simplification or right amplification, because this happens rarely. Okay. So far, this is still simple. There is going to be a problem, as we're going to see. Okay, so what's one downside with this whole approach? Yeah. Yes, why? Because
like the different data blocks are in different cache lines.
Yeah, So there, yeah, okay. So there are different cache lines. So things are no longer contiguous in case we want to scan this. But also, we now have to do 2 memory hops for every access, right? We have to go through the directory first. We might incur 2 cache misses instead of 1 cache miss, right? So this could damage our performance. Okay. So how might we want to mitigate that issue? What do we want to guarantee about the directory? We basically want to guarantee that it stays small. And when I say small, what I mean is I want the directory to always be able to fit in the L1 cache. Okay, so what's the best that so how do we do this? And like, okay, so what are the risks? Okay, so far I've assumed that all the data blocks have the same size. Assuming that all data blocks indeed have the same size, right? What's the size of the directory? The size of the directory is just going to be something like the whole data size divided by the data block size, right? That might be okay in some cases, but what's the risk? Right, the risk is kind of the following. The risk is that, suppose that I set the initial data block to be too small, right? The directory is just going to continue growing linearly with data size. So that's the thing that's not so ideal, because if it's growing linearly and the data is growing by a lot, the directory is just going to grow and grow and grow and continue to grow until it might eventually exceed the L1 cache. And recall that the L1 cache is not that big, and the L1 cache also stores other things. It's a precious L1 cache is a precious resource, right? We don't want to butcher it or abuse it. Okay. So we care about the directory not outgrowing the L1 cache. How might we do this? Yes. Okay, that's an interesting idea. What's the issue with that idea? So in particular, think about space simplification.
One block, like that's like maybe choose 60 or something, we'll have just one item.
Exactly, yeah. So if you're using that approach, you're going to have like immediately a space simplification factor of at least 2. Not ideal. Yes?
Add another directory under the top level. So like kind of similar to memory translations, like L2, L1, like multi-level space tables.
So nice idea as well. What's the problem there?
The top level might fit in L1 cache,
Yes.
and the bottom there is
Exactly. So maybe you've like delayed the problem, but this doesn't make the problem go away. Yes? You want to do a linked list once again? Okay, so basically the directory will still continue to grow, but as a linked list. Okay, but if we do that, that doesn't, so the problem that we were trying to address is that the directory is growing linearly with data size. With what you're proposing, it's still going to grow linearly with data size, right? That's the problem we're trying to make go away. Other ideas? Okay. So Vijay, you had a nice intuition. You wanted the arrays to be growing at an exponential rate, but we saw that the issue with that was space simplification. We can still use that idea and try to get the data blocks to grow as a function of data size. If the data blocks grow as a function of data size, that does actually mean that the directory will grow at a smaller rate, but maybe we don't need to be exponential, right? About how fast we grow. Maybe we can grow at a slower rate. Okay, so that's what we'll try to do. Okay, and these insights come from a paper from 99 called Resizable Arrays in Optimal Time and Space, okay, from Algorithm Data Structure Symposium. Okay, and this is kind of a high-level idea of what this looks like. The blocks are growing in size. And this indeed also means that the directory is going to grow more slowly too. The question is about rates. So now it becomes a game of like, by what, how much should these grow, and by how fast does that cause the directory to grow? So these are things that we'll now try to analyze. Okay. What we're going to aim for in this design, now I'm just giving you the high level. What we're going to aim for is for the number of data blocks in the system to be square root of n. That's going to be the number of data blocks. That's also going to imply that the number of pointers in the directory or the size of the directory is going to be square root of n. Okay? What does that imply? That implies that whenever the directory expands by a factor of 2, right, this just becomes 2 times square root of n, big O stays square root of n. Okay, that's okay. I am then also going to guarantee to you that the size of the largest block is not going to be exponentially larger, but it's going to be basically proportional to square root of n. What does that mean? That means what does that mean about space wastage? It means that when I allocate a new block in the system and that block is size square root of n, it means that I'm wasting at most square root of n slots in the largest array. Okay, so basically I'm wasting at most square root of n here, and I'm wasting at most square root of n here. So overall, I'm wasting at most square root of n. Does that make sense? Cool. Okay. And that's going to give me this kind of guarantee. Okay, that overall my space simplification, this is not actually space simplification. This is actually measuring max, sorry, this should not have been, this is just max wasted space. Okay, okay, so that's the promise of the design. Okay, so far there's some nice promises here, right? So the promise is to really restrict space simplification to be like sublinear with respect to data size. And also we get to expand the array without copying everything, right? So we do still have a promise here of a right amplification of 1. So far, right, this is kind of really nicely addressing everything we're trying to do. But it leads to 2 challenges, right? And the first challenge is how to actually, what does this look like in detail? Like how, so, you know, how do we actually grow these? But also, how, you know, for given that we now have an irregular block size, for a given get operation, how do you infer which data block to go to and which slot to go to? And how do you do all of that really, really quickly? Okay? Good. Yes.
I was looking at widespread loop.
Sorry?
Like widespread loop, maybe not something smaller. Or like log, for example.
Great question. Why do you think? It actually turns out.
I haven't really thought of widespread specifically.
What? Okay, so this is a really nice question. It turns out that there's a lower bound that says that you can do better than this. Let's reason about why. What happens if you set this to be larger? Right? If you set this to be larger, the directory is going to shrink. So you'll be wasting less space in the directory, but you'll be wasting more space here. On the other hand, if you set this to be, you know, smaller, what's going to happen to the directory? It's going to be bigger, but then you'll waste more space in the directory. Right? So there's kind of like a contention between how much space you're wasting here and how much you're wasting here. And that kind of implies that you can't really, with one level of indirection, you can't do better than this.
So it's also, if we had, you know, big enough caches, maybe adding more directions can lead to better around.
Yes, but it's also going to lead to worse query performance. Good, excellent question. Yes.
The waste space in the directory level is going to assign pointers, while
Yes.
level below is based on the size of your elements in the array. Secondly, you might be wasting much more space in the lower levels.
Okay, I guess I'm
You might
assuming.
decide them according to the ratio between pointer size and elements. This is a hunch. I don't know.
Okay, so one assumption that I have is that like I'm filling up this array sequentially, right? So I'm assuming that so by the time that I allocate this, I'm assuming that all of these are full.
Yeah.
Right, so I'm only wasting space here.
Right, but the size in which you need to allocate this space is some integer of the size of the basic element you store in the array. But the directory only has to grow based on how many more pointers you would like to store. So there is a size range between the pointers and the elements, which means that you may be wasting more space in the slots compared to the directory.
I mean, so, right, as we kind of said, that there's kind of a trade-off between them, right? It's like do you want to say something related to this?
Like if you're just trying to store something really big in like the lower, in the actual like way, you're gonna be using pointers for that. And
Not necessarily, I'm just saying, the way we formalize the problem, pointers are necessarily pointers in the directory. Slots are the elements you're going to store in the array. I'm just wondering if you were to parameterize the ratio between the element size and the pointer size, would you be getting something else and not square root?
Sorry, what do you mean? What do you mean the element size? Like, do you mean like the
So
size
I
of the
have
slot?
Array of strings of size of 5 chars or strings of size 20 chars.
Ah,
I would be wasting more space.
okay. Now I see what you're saying. You're basically saying that, like, okay, so you're right. I guess so far I've assumed that the size of a slot in the directory is the same as the size of a slot
Yes.
in the array.
The ratio might affect.
Okay, I completely agree with you. Yes, so in a real setting, I might want to take this into account. Thanks for the point.
So if I understood this correctly, like for the sake of this easy example, the n is the number of total slots, right? Is that correct?
The end is,
The n, like, right now it's all square root of n pointers.
Yeah.
N from the square root of n being the total number of slots within this dynamic array. Is that correct?
like, the total space wasted.
No, not total space, but it's just the total slots.
The total number of slots is basically the sum of slots across all of these different arrays, yes. That's gonna be n, yes.
That's it, okay. So if the n is 4, which square root of 4 is 2, up till the point, up to like you're inserting 4 slots, you're only gonna have 2 pointers. And when you add a 5th slot, at that point, you're gonna create a new pointer, because that square root of 5 is gonna be, well, greater than 2, it has to be a whole number, so it's 3. And then you're going to add square root of 5 slots, which is gonna be 3 slots.
Okay, I think you're basically trying to play out what this is gonna look like in practice.
yeah.
And I think that you're kind of spotting that immediately when you start this thing, the guarantee maybe doesn't hold, right? Is that kind of what you're saying?
Not that the guarantee, I just wanna understand how it actually works in practice.
Okay, so we're gonna see that in a second, but by the way, to that point, the guarantee doesn't actually hold immediately. The guarantee is gonna hold as we move along.
Yeah.
Okay, let's actually see what this looks like in practice. Okay, so so there's a promise, there are the challenges. Okay, so here's the actual construction. We're gonna have multiple levels, right? But so these levels are gonna be conceptual, and these levels are gonna be exponentially increasing, sorry. And each one of these levels will allow you to store multiple data blocks, and we're going to see exactly how. Let's say level 0 always stores an array with 1 slot. And then for every pair of subsequent levels, we're going to do the following. Right, so for the next level, we're going to double the length of the arrays relative to the previous level. And then every second level, we're going to double the number of arrays, or the number of data blocks. Okay? It looks a bit strange. So based on these two rules, what should I expect to have here? How many arrays and of which size? 2 arrays of 4, correct? And here? 4 arrays of 4. Yeah, and this is going to continue and continue. Okay, so regular construction, a little bit quirky. Okay, so with this construction, we can actually reason pretty easily about the number of arrays and the size of the arrays in each one of the levels. Okay, so, you can, it actually happens to be these numbers, right? So there's going to be 2 to the power of k minus 2 blocks in each level, right? Where k is the level ID. And each one of these arrays at level k, they're going to have this number of slots. Okay, so I added these just so you can verify that this actually works. Okay, this was for the blocks. This is for the number of slots in each one of these. Okay. So, okay, so yeah, so the total number of levels that we have here is log of n. How many data blocks do we have? Okay, so I gave you the promise that the number of data blocks should be square root of n. Let's actually test whether this holds up. Okay, okay, so we know that the number of levels is n. We know that, okay, so our insight about counting the number of data blocks is that most of the data blocks are at the largest level, right? Kind of asymptotically most of them, right? The exponentially fewer data blocks at smaller levels. Okay. Now we know that at the largest level, right, there is this number of data blocks. Okay. So this is level k. Let's plug in log of n. So there's log of n levels. So the largest level is log of n. Let's plug this log of n for k. Right? And simplify. And if you simplify, you indeed get square root of n. So this shows you that at the largest level, right, we have square root of n. And that's where most of the data blocks are asymptotically. So this is where you get your square root of n bound on the number of data blocks. And this is also why the size of the directory is square root of n, because you need one pointer for each data block. Okay? Yeah.
Why square root and why using 2 instead of doing cube root or fourth root or fifth root or like 1.3?
So the intuition for using square root is that you're really trying to balance out the amount of space. It relates to the lower bound question. It's really about like trying to balance the amount of space you're wasting in the directory versus in like the largest data block. Right? And like there's that trade-off there. Like the smaller you set, if you want to set the largest data block to be smaller, there'll be more data blocks in the system, the directory will grow. Right? If you want it to be, if you want the final data block to be larger, the directory will be smaller, but you will waste more space at the final data block. So it's really a balancing act. Is there a comment there?
Yeah, I think you could say the product between the largest block size and the size of the directory is a linear function of n. The largest block is 100. You're going to have at least n over 100 blocks. So you're going to have to store at least n over 100 pointers.
Right.
So the product has to be linear. And that is minimized when each of these is square root.
Okay, so this is the like so there would be like a graph in which the optimized value is.
Yes, exactly. Now you could do better if you add more layers of indirection. But that's going to damage your query performance. And I'm not even sure that that would help you, to be honest, because with more layers of indirection, right, Joanna, that wouldn't necessarily help you. Yeah, so that's probably the best you can do. So by the way, this is for everybody, this is Joanna. Joanna is visiting me this week. She's a world famous theoretical computer scientist. So she can answer anything that I cannot answer. Okay. Okay, so this gives you the guarantee of square root of n. Good. So now this is basically our guarantee over the size of the directory. Let's now get a guarantee over the amount of wasted space at the largest block. Okay, so to do that, right, we know from here, this is the number of slots in a data block at level k. All right, so we're going to take this expression and then again, like plug log of n because we care about the largest level, and the largest level is log of n. Right, plug that in, and again, you get square root of n. Okay, so both, right? So the size of the directory is square root of n, the amount of data wasted at the largest block is square root of n. We're good, right? Just meets what we require. Okay. Okay. Is that good with everybody? Good. Okay, so here is what the directory might actually look like, right? So the directory has a pointer to the beginning of each one of the data blocks, right? So, you know, this one is pointing here, this B is pointing here, C and D are pointing here. Now we're going to look at how, okay, right. So this is just finishing the analysis of space simplification. And okay, so this is the total amount of wasted slots if you want to express that in terms of space simplification, you can actually express it in the following form, right? 1 plus the inverse of square root of n. And interestingly, this thing is just as n grows, we observe that the space simplification is actually shrinking and shrinking and shrinking, right? So this is great for us. This is great for us. It means that, you know, it's going to make it much easier for us to make sure that the directory is able to stay in the L1 cache and that we're not wasting too much space as well. Okay. Okay. So that's the construction. Now let's look at the question of how to actually handle queries. Okay, so to illustrate the problem we're trying to solve here is, suppose we have a get for, you know, slot number 12. There are a few things that we need to do here, and we need to do them fast to get to the slot containing the data we're looking for. First of all, we need to infer how many data blocks we need to skip at smaller levels, because that's going to correspond to the number of pointers that we need to skip in the directory. Right, that's the first component. Second component is we want to figure out within the target level how many data blocks we want to skip, right? We're going to add that. So here, you know, we have to skip 1 data block here. And third, okay, so then, you know, we might follow a pointer over here to this data block. And finally, we need to also infer how many slots we want to skip within the target data block. Okay, these are the 3 things we need to handle a query. Okay. And the question is how to do these things super fast. Because remember, our competition here is just a plain old array where we have random access with no overheads at all. We're trying to come up with a replacement to it, and it's not going to be practical if this is CPU inefficient. And so we want something really, really fast, definitely constant time, but also very, very fast in terms of hardware implementation. So how do we do this? Okay, we're going to do this in multiple steps. So let's first of all talk about the first problem of inferring how many data blocks there are at smaller levels, right? So how many blocks do we need to skip from how many points do we need to skip from the beginning? Okay, so how do we do this? So first of all, our first step is going to be to identify, based on the slot ID that we're trying to get, we're first of all going to infer what is the target level that actually contains that slot. What is it? Yeah. Correct. So in particular, it's, I mean, there's a +1 here. Don't worry too much about it. It's some rounding thing, but it's what you said. Okay. So just to check that this works, right here, if you take this 12 and we plug this in here, we get 3. That's indeed the target level where the slot resides. Okay. The issue is that a log function is slow. Right? So if we have a log function and we start putting all these expensive functions in our query path, it's going to slow things down. It's not ideal. So we might ask, how would we do better? Can we compute this log function using some bit arithmetic rather than actually relying on a complicated function?
A bit mass on the, it's like everything just like Carlsson to like representation.
So what kind of bitmask would you want to use?
The number I plus 1, that represents the binary format. So it's the highest bit from the left.
So basically, you're trying to reduce the problem to finding the location of the most significant bits. Exactly. That's not actually something that we're going to do using a bitmask, but we are going to do it using an efficient CPU command. Okay, so with that insight in mind, okay, so the first problem is the log. Second problem is like this typecasting. That's not ideal as well for performance. Let's get rid of both of these. And you gave the correct insights. Log base 2 actually just kind of amounts to finding the index of the most significant bits of an integer, right? And we can do that in the following way. Take the size of the number of bits in the integer, subtract 1, and then, you know, this is a nice, cute command that counts the number of leading zeros of an integer. All right, so if you do that, that basically amounts to this function. And this is very, very CPU efficient because counting the number of leading zeros, this is 1 CPU command, 1 CPU cycle. All right, this is also quite efficient. So Okay, and this is right. So this is the integer length in bits. Okay, yeah, and this is your specialized CPU command. Let's just see how this works in practice. Suppose you have 8 bits for this integer. This is the bit encoding for 8. And indeed, this is the length of it. The number of leading zeros here is 4. And indeed, you end up getting 3, right? Just so that you see how this works. Okay, and we tested this. Young Min, our student over there at the back, said actually benchmarked both of these functions and found that this function will take you something like 1 nanosecond as opposed to something like 7 nanoseconds. All right, so this is a significant difference if you have, right, if you care about high throughput. Okay, so that's the first step. We did the first step of figuring out what the target block is. The second part, we're still at step 1. We're still trying to figure out how many data blocks there are to skip in small levels. Now that we know what the target level is, we want to use the target level to figure out how many data blocks there are cumulatively in all the smaller levels. Okay, so now I'm going to throw a function at you, and I'm just going to tell you it happens to be this. It happens to be this. And I'll also make one note about this function. The original paper actually gets this wrong. They have a mistake. It's inaccurate. So I give credit again to Young Min for actually correcting the equation and coming up with something that actually works. What's the intuition behind this thing? Why is there a mod in this function? So this is something that, if you sat and thought about deeply, you would be able to derive as well. But let me just give you one quick intuition. Why is there a mod here? So actually, does somebody have the intuition for why the mod is here? Mod-based, mod 2? Yeah. Yeah, that's basically the intuition. The intuition is like the number of like additional runs grows every 2 levels, right? That's why you get that there. Okay. Okay, so so now you can take that. So if you want to, you can verify that this actually works. You can take this equation and compute number of, so for each one of these, right? So for level 3, this will tell you that there are 4 data blocks at smaller levels, and you can kind of verify that this actually works. Okay. Okay. This equation is actually not so much my point. My point is that this equation, even though it works, so we want to compute it fast as well. What are some things that might be slow to compute in this equation? Well, first of all, we see that there's a modulo here, and we see that there's a division here. Division is generally considered to be pretty slow. What other problem do you see in this equation that might be slow to compute? Huh? The floor, yeah. So the floor also might involve typecasting. One more thing. Sorry? The exponential, yeah, exactly, right. So the power is also not going to be trivial to compute. I think actually, as far as I understand, a power function is not constant time, right? It has a complexity that depends on the thing that you're taking the thing to the power of. Okay, so we want to compute this expression, but we want to do it quickly. So how much you take this expression and speed it up? With which one? Oh, for this one, yes. Yes, that's right. Okay, so first of all, the insight is actually whenever you have division of or exponentiation with with factor of 2, these are always operations that you can speed up with quick bit tricks. And as you said, the first thing that we can do is take the small operation, right? And this is what you said, right? To end it, basically end it with 1. Okay, that's the first step. Second step, what can we do? Second step, what can we do with this thing? How do we take this and do this using bitwise commands? So yeah, right shift by 1, exactly right. How about the power? Yeah. Correct, left shift. by this amount. Okay, so we took this command, we converted it into something that's now very, very easy to compute, very efficient to compute. We benchmarked this as well, again, thanks to Youngmin. And this takes you something like a half a nanosecond to compute as opposed to something like 10 nanoseconds. Okay, so these things end up mattering if you really care about high-speed code. Okay, and like the deeper kind of insight here is that, anytime that you really care about high performance, if you can actually reduce the operations that you're trying to do into, just log base 2, powers of 2, divisions by 2, right? This is going to be an algorithmic design tool that will allow us to then compute things super, super fast in terms of CPU efficiency. And that's what's happening here. Okay. Yeah.
This expression defines itself.
Yeah, it's slow.
All of the other parts is very deep. All of them are piecewise operation, basically, and also the
You're right. Sorry?
Compounder doesn't sell the multiplication. Yeah,
You're saying the compiler will be able to help us here, or?
I'm sure. No, I'm just saying that this is a super efficient spread. Probably minus
I tend to agree with you. So so the fact it still took us like less than nanoseconds to compute, but so you're kind of reaching the limit of my knowledge, I guess. I agree. I believe that subtraction is slower than all these other operations that we're trying to do. I don't exactly know by how much, but I believe that subtraction still takes not too many CPU cycles, right? So I mean, really what we're trying to avoid are complex functions like log and power. Here you actually have to invoke another function. We're trying to avoid typecasting, and we're trying to avoid divisions, right? These are the core things that are really, really detrimental. I guess as a rule of thumb is, if you have some subtractions and additions, it's not too bad. Also from the experiments here. But it's an interesting question whether you can also get rid of the subtraction here. I don't know.
0.6 nanoseconds is a very small number.
So ask the man next to you. So can you say that more loudly? Can you speak up? Yeah, why don't you say it now?
I used a third-party benchmark, and I executed the equation multiple times, and then I divided by the number of executions to amortize the cost.
What's the benchmark you use called?
It's called
Nanobench? Okay, so Nanobench people. Okay. Okay, so we're almost done. I've kind of shown you the main points. Just for completeness, I'm going to finish this to show you, completely how queries are handled. But really, so far we've seen the most important insights behind all of this. What we want to do now, so now we know what the target level is, and we know how many blocks to skip in previous levels. What we want to do now is handle steps 2 and 3. So step 2 is to figure out how many data blocks to skip in the target level. And we want to figure out how many slots to skip in the target block. For here, I'll actually just kind of give you an insight. So it kind of turns out that, if you take the slot ID, you just add 1 to it, and you express the bit the bitwise representation for it in binary. So let's just kind of show you. So it turns out that the next most significant bits, right after the most significant bit, actually just give you the ID of the data block within the level that you're looking for. And then the subsequent bits after that just happen to give you the slot ID. So just to kind of give you an example, here's our 12, binary representation for 12. I'm just adding 1 to it. And then I'm taking that, right, and dividing that here, right? These are the most significant leading bits, and this is the most significant bit. So as I promised you, 1 bit after that gives me the block identifier within the level. That's 1. And I know that I need to take just 1 bit because I know that I only have 2 data blocks here, so I only need 1 bit to identify it. And then the subsequent bits, right? And 2 bits to identify 4 slots, right? Gives me slot 1. So that's here. Okay, so this is something that you can verify. So again, just for completeness, I can reason about the number of bits that would identify the block, the number of bits that would identify the slot. And then basically, I'm going to gloss over this part, right? But basically here, I just need to do some bit shifts and to take some masks to basically extract the data block ID and the slot ID from this I+1 expression. Okay, so here I'm computing the slot offset. To compute a slot offset, I'm computing a mask here, and this mask is getting rid of everything but the least significant bits that identify the slot. And here I'm computing the block offsets. And again, just to give you the quick and dirty intuition, first of all, I'm going to shift these block identifiers all the way to become the least significant bits, and then I'm going to take a mask that's going to get rid of everything else. Okay, so that's my mask. Okay, and now I'm done. All right, and I'm done. And this is just to illustrate that even these last steps as well, I can do all of these steps using very efficient big tricks. Okay, so now we're done. Now we can kind of conclude what we have learned. What is the map of everything we've seen in this class? And okay, so here's our analysis table of all the different metrics with this approach that we've just explored. Our right amplification is something like 1. It's actually slightly higher than 1 because technically the directory does expand, and when the directory expands, you are copying what's in the directory, but it takes a long time for the directory to expand. So basically, this is really, really near 1. Okay, our space simplification is 1 plus 1 divided by square root of n. So this is shrinking as a function of data size. And our read amplification, well, it's not quite 1. It's now O of 1. We have to do some work. But as we saw, we're making sure that the directory fits in the L1 cache, and we're making sure that all of our CPU operations are super efficient. And so, you know, we're still doing pretty okay. You can compare that to the things that we saw before. So if we don't have any indirection and we just have a contiguous array, right, this seems to be the best we can do, right? So this is our right amplification, this is our space amplification, and our read amp here is just 1, not O of 1, right? But here, right, so here there's a trade-off between space amplification and right amplification. Note that our solution with indirection completely gets rid of that trade-off, right? And if you want to be more detailed, right, you can also analyze it, with, if you have the contiguous array and you're expanding by more than the golden ratio or less than the size of ratio, right, you get these different properties for space amplification. Right, and this kind of concludes all the different trade-offs we've seen throughout the class. And that is the conclusion of the first lecture. So thank you very much. And